Hello. The plan for today is to add arrays to our C interpreter. Now, arrays in C are a bit special because essentially arrays aren't really first-class types. So when we have an array of some size, the array object doesn't behave like any other object, like an input. So for example, we cannot return an array from a function. And essentially, every time we use an array, it implicitly converts to a pointer to the first element. So when we write something like so, the array here on the left-hand side gets implicitly converted to a pointer to the first element, and then we do essentially arithmetic on that pointer. So you can also do like this. So you can dereference an array and have it behave like that. And this means that we need to add essentially a new kind of conversion to our AST. And the standard says something about that in general. When we have an lvalue. So when we have an lvalue that we aren't using in a situation, I'm talking about this paragraph here, that we aren't using in a situation where we require an lvalue, like taking its address or incrementing it or modifying it, it gets converted to the value stored in it. So this is an lvalue conversion. So essentially, what we're doing, let's just do something like that. So here in the AST on the left-hand side, we are using the identifier expression, which is an lvalue. And on the right-hand side, we're also using the identifier expression. This is technically incorrect. What we need to add a conversion that converts the lvalue, I, into the value currently stored in I. And this sort of conversion is then also be used for arrays. So same paragraph for arrays, unless we use that as a size of, it gets converted into a pointer to the object. And this is something then we can also hook into that conversion. So let's start by implementing the lvalue conversion. So got I think it's a cast expression, yes. Let's add it below. An lvalue conversion that converts an lvalue expression into its value. So it's a node lvalue conversion expression inheriting from expression. And essentially has the same interface as cast, so we can copy that. And then we need to add the node kind as well. So cast expression, lvalue conversion expression. Okay. And now we need to add printing support for that. So when we do the cast expression, lvalue conversion, we also dump its type. During CodeGen, we don't need to do anything. Or essentially, so how do we handle CodeGen currently? So when we get an identifier expression, right, that can be done. So currently we're having, in CodeGen, we're having two kinds of expression, CodeGen expression as an R value and then CodeGen as an L value. This pushes the address of something. And then here in the identifier expression, we're essentially getting the address and then we're immediately loading its value. So what we can do there to change that is we can do CodeGen the identifier here as an L value. And then we separately do the load here in the lvalue conversion expression. So when we have an lvalue conversion expression, we can, at this point, the address of the lvalue has been pushed onto the stack, load the value stored at that point. So what we can need to do is get the type, load them in load field of that type. So lvalue conversion gets the address, gets its value. That's what it's doing. And the pure lvalues, so identifiers, only get the actual value. So another lvalue is deref. It's on top of the stack. No need, right? So all it does is dereference it, but this is now done by the lvalue. No need to do anything. Lvalue conversion dereferences it. Let me just double check that we are handling all lvalues. Yes, identifiers and deref are lvalues. Okay, so now all we need to do is in the AST, we need to create the conversion if necessary. So if the expression is an lvalue, get creates an lvalue conversion. So do lvalue conversion. Compiler state lvalue. So if is lvalue. Let's just call it expression. So if we have an lvalue, or that if we don't have an lvalue, then we return it unchanged. Otherwise, we return. How do we add the conversion node here? Alright, we can just like so. So otherwise we return an lvalue conversion expression. I need the location. We keep the type the same because we like when we load an lvalue, we keep it type. But wrap it in the conversion. And now we just need to insert the call in the various expression parsers. So built-in expression doesn't need to worry about that, I don't think, although it does use, so it gets a child expression, which means that we need to do an lvalue conversion here. Because we're not using it as an lvalue. So essentially every time we use an expression, not as an lvalue, we need to create an lvalue conversion. So like here, although not always. So if it's an address, we don't want an lvalue because then we actually use it, right? So except for size of, type of, address of, increment, decrement, we don't have that one, or assignment. So address deref. So when we dereference a pointer, it also gets converted to an lvalue. When we use it like and then we need, if it's not increment decrement, unary up post inc pre-inc decrement decrement. Then we also need to do an lvalue conversion. So this is the size of, and we don't do lvalue conversion here. No, wait. This is a line of with a type. Then we don't have this one anyway, and this is size of, there we don't do one. Okay. This is cast expression, I believe. Yes, cast expression does lvalue conversion. This is function call. Function call does an lvalue conversion. Then continuing on, we've got array access. We don't do an lvalue conversion on the left-hand side, but we do one on the index. So we need to convert the index. If it's an lvalue, we need to load its value. That's what we're currently doing. So state, location, index, converted into an R value. Okay. Unary is done by the function. Arithmetic does lvalue conversion for both. State, location, left, right, right. When we have, what's next? Comparison, same thing. For sequenced, so comma and or, we also need to do, don't use them as lvalues. But for assignment, the left one stays as an lvalue, but the right one does lvalue conversion. Here, so on the ternary operator, nothing is used as an lvalue. The ternary operator in C, the ternary operator, the results can be an lvalue, but not in C. So that is not an lvalue. Okay, it's a bit, I think it's a bit weird that the lvalue conversion gets rid of an lvalue and turns it into an R value. But okay. Right, it helps if I call the constructor correctly. I need to give you a name. So this is the lvalue conversion. Lvalue conversion expression, which converts stuff into R values. Child, oh, right. We need to convert the function. And then we need to convert each argument. State log argument. The location of the call here. Okay. This one seems to work. Let me see whether we are. So print I. So as you can see that on the left-hand side of the assignment, we keep the identifier as is, but on the right-hand side, we add the lvalue conversion. The lvalue conversion then causes the load instruction of the actual lvalue, and then we continue on. The interesting thing is whether the tests pass, and they do not. Okay, so assignment.c, assertion at line 8 fails. Compound assignment. So what do you do? Assignment expression. we don't, so for compound assignment, the left-hand side is kept as an identifier expression, even though it should be converted into an L value. We need to trigger. So the issue here is because the plain identifier expression during codegen no longer loads the value, it produces the address. So we get the address of the value and then we add 2 to that. We don't get the value. So we need to add an L value conversion here. So, but we don't have space for that. So we need to adjust the AST for the, my language server died. The assignment expression, that's a bit annoying. So currently the assignment expression stores the operand and then the left and right operand. But for the left one, we sometimes need to trigger an L value conversion and sometimes we don't. I believe let's special case that in codegen. That's the easier one. Right. So when we do, we sometimes have assignment expression right here. So push the value we are assigning. Right, then we codegen the L value. Right here. So we need to visit the left operand. Let's say I'm pretty sure the left one, let me restart so I get the language server back. So the left one is always the L value. I'm pretty sure. So CLOF is L value. The left-hand side. LIS of assignment should be L value. This means that evaluating the L value gets the address, not the value, since we are lacking an assignment expression. Not an assignment expression, an L value conversion expression. Manually do that here. So this is simply type, codegen type, expression left type, and then love build load the field. Type. Okay. And now we should get 2. Let's see what that does for the tests. Okay, progress, global.c, line 16. It's probably something to do with increment. I would guess, and not to do with globals. Let me see. Yeah, why are we printing 3? That doesn't make any sense. So what we're doing, so we've got a unit expression pre-increment of the L value I. That makes sense. I believe because we also unit expression right here. So because we are also lacking the L value conversion at this point, we first need to load the value. First load the value. Since it's an L value, the address is on the stack. Load other inst load field b type 0. Then we add subtract 1 with the arithmetic built-in. Then we save a copy of that into the L value. Why is the address? I'm not quite following the logic right here, because the address is on the values on top of this. Where's the address being stored? Store the, right? There should be an address somewhere on the stack. I'm not quite seeing where that happens. What do we generate? Not quite correct. So we've got local allocation. We are pushing 0, we're storing 0 in 0. Right, we are getting the address, we are loading the value. Then we're pushing 1, calling add, duplicating the value, storing that. Then we are popping it. I don't quite see why that works. So why are we getting in line 4? We're getting an invalid address in line 4. So all right, so why, like this store instruction? Oh, because we are doing a codegen. I see. Okay. So this pushes the address onto the stack. Then we are loading it. Then we are adding subtracting 1, right? And then we need to yet again get the address. Like so. Okay. Apparently not. All right, I don't need this type. I need here. I need codegen type. Okay. Because it's an L value, the address is on the stack. Dual load to get the value. Okay. Then we add subtract 1, and then we can add a copy. Okay. Now this should work. Yeah, we're getting 1. So now we're getting the value, adding 1, storing it. Okay. And same deal here. So we first need to load to get the value. And then we are storing it again. Okay, progress. So now we're failing in heap. Also failing in if and in mutual recursion and in void. Void seems like the simplest test case to debug. I'm assuming this is all the same bug. So we are failing. No longer failing. No longer failing. Failing. Interesting. Why does this one fail? So we are in codegen lvalue. Okay. So codegen lvalue for an identifier expression does not get. I accidentally removed too much code. So the previous one right here, this one, also handled code for functions, which we're no longer doing here in codegen lvalue, because I guess it makes sense that a function isn't an L, well, I mean, it's kind of an L value, it has an address. So that's the edge case, I think. Not the type of a variable. Okay. 98. Not the type of a variable. Well, I mean, it does. Yeah, I mean, that's true. So the assertion is that we are asking to get the type. Wait, why do we want the type of a function? In lvalue conversion expression, right? So we want to convert the function into an lvalue. So for that we need the type. Okay, so we don't actually need to formal. So we get the address of a function, and we want to get its value. But the address of a function is the value on its own, so we don't need to load it. So if lvalue is complete object type, then we need to load. We need to load if it's an object. If it's a function, it's already the value. Because as I said, the value of a function is its address. Okay. So almost there. And then we finish that refactoring here. Line 58. Okay. And it's good that the assertion called simple while fails. That makes it quite easy, because it's presumably the simplest while function. Let's print it. We're getting 3. Okay, that's a bit odd. Why are we getting 3? So in the simple while function, we are storing the parameter in address 0. Then we are storing 0 in result. Then we are loading the parameter, comparing it against 0. If it's less or equal to 0, we're going to an A, which means return. So what we forgot to handle is return. The return statement uses an expression as an R value, not as an L value. So we need to insert an L value conversion here. So return statement. Here we go. Expression do L value conversion. State pulse expression. And now we should get 0. I believe, yeah, no, that is correct. Let me see whether there are other statements that take an expression. So we've got the deckel statement doesn't. The expression statement is an expression on its own. So I'm guessing, right, the expression statement, I mean, it doesn't really matter. So because we are not using anything with the value anyway, so it doesn't matter whether we get the address or the actual value. So let's not worry about that. Break statement doesn't, continue doesn't. If, right, the condition in if and a while also needs to be do an L value conversion. Block statement does not. So the if statement, it's annoying that I can no longer use. So let's create a wrapper. Start expression as R value. What we're doing is we're parsing an expression, and then we are getting an expression back. So we're getting the compiler state. But we also get the position. And then we're returning to lvalue conversion, state position expression. So this passes an expression, it gets it as an lvalue, and then we're using it here as r-value. Let's also use it here, because why not? R-value, and then we don't need this conversion here. And then inside if, we can pass the condition as an r-value, and we can pass the condition as an r-value. And with that, we get pass tests. Okay, so let's commit that. Add lvalue conversion to properly model lvalue to r-value conversions. Yeah, I believe in C++ it's called lvalue to r-value conversion or something like that. Okay, now we can add arrays, because arrays make use of the lvalue conversion to decay to a pointer to the first element. So arrays are a new kind of type. So we've got a pointer type, a function type, let's add it here, array type. So an array type an array type. Useful comment, array type. So it has an element type. There's an element type. And then it has a size, which is an expression. Which is a bit annoying. So I could add a parameter, so I could do something like forward declare expression and add the size as an expression. But this is problematic for multiple reasons. For once, we want to like intern types that are identical, and we don't want to compare expressions for equality. We want to compare the value. So it makes sense to directly store the value instead. So it has a size. Size, private, size t, size. Standard size t, size. Okay. So that's an array type. Array, we first need to add it here. Then we want to hash the size. We don't need to add the child type, that is done automatically. Size. And then we also need to compare to arrays for equality. And again, by only comparing the sizes, because the children are compared false. So arrays are equal if they have the same size. We want to clone arrays. Array type by cloning its element type and copying its size. They don't participate in make unsigned in the same modulo qualifiers. They are not void. They are signed. They're not arithmetic. They're not pointers. They're not scalars. They are complete object types. Yes, they are not pointers to complete object type. They don't have qualifiers. They don't have an integer rank. This is part of expressions, but they can be printed. So somewhere I can print types, and array type. So I want to print them like so. Yeah, let's try that. Okay. So that's the array type. Array types can be declared using the array declarator. The grammar is a bit complicated because C has these features where you have an array as a function parameter. You can specify like what sort of size you expect, and then you've got like a static qualifier, and you can const and so on. We are all not going to support that for now and just have the syntax direct declarator, angle brackets, assignment expression. So that should be easy to parse. Declarator. So we've got pointer declarators, function declarators. A declarator, yeah, is an array declarator. I don't exactly know what the correct precedence here. So we've got the function declarator whose operand is a pointer declarator. Because it's a postfix, that's also a postfix. I believe we can handle it the same way as we can handle function declarator. So the type is array declarator, which we first need to add. No, that is our tag, never mind. And then we've got the angle bracketed, no, not angle bracketed, square bracketed, DSLP assignment expression. And the operand is a direct declarator, or which is an atom in our case. And then we've got, here's where it gets tricky. So we have a callback that gets a state, child declarator, the tag, and then we get an expression, because that's what we're parsing. And now what we need to do is do constant evaluation of that expression to get its size. We can do constant evaluation. We are just not exposing it at this point. So let's add a to-do just so we can get something compiling. Constant eval expression. And instead, first of all, add an array declarator. Array, it's a container node of declarators. It has a child, and it has a... Actually, at this point, we don't need to evaluate the expression because we might as well. So we get the size already evaluated. We don't have parameters. We just have a size. Okay. Size. Then I need to add you here. Array. So that's the array declarator. But now let's hardcode the size to 0. Child expression. No. Child 0. And then we need to update some functions regarding declarators. I believe then the AST type, get type, right, those ones. So for an array declarator, we are getting the name of the child. It doesn't have an initializer. They do participate in the type. So array declarator, if we want the type, what we need to do is get the child type. And then we are building an array type. Create lvalue array type with the child type and our size. Okay. Let's see whether we are compiling. We are not. No matching constructor. So we give you a child type and a size. Why do you not want that? Oh, right, I need to clone the type. Clone the child type. Okay. So we're compiling. Let's see whether we can parse it. So int array. Apparently not. Declarator. I think I know why. So the operand of function, let's say it's an array declarator. Actually, I believe they sort of have the same precedence. Yeah, I think they have the same precedence actually. What does the grammar say? So we've got declarator as a, yeah, that's sort of like, this isn't really written in like sort of like there are operators, but it's not really written in a precedence style. But I think they're on the same level. So let's call this one postfix declarator. And support both operands in one. So this is a postfix declarator. Postfix fix declarator. And then here we go. We can distinguish, so if you've got an expression, it's an array. If we got a parameter list, it's a function call, a function type. So that should parse it correctly. But we're missing a visitor somewhere in printing, I'm assuming. What are we trying to do? Let me try that again. We are trying to create a declaration. Right. So if we're having an array declarator, we're also creating a variable, not a function. That's what's missing here. Right. This assertion is encoded, but we are generating correct thing for now, except for the size. So we need to do constant evaluation of the expression to get the size. So for that, we need to expose an API to do constant evaluation of integer expression. Constant eval integer expression. This requires a VM. I'm not sure whether I can actually get you the AST at that point. Because it's incomplete, I'm pretty sure. Yeah, so it's missing like the tree and the roots. Do I need the AST? I don't need the AST and use the AST to get the symbols and the locations. I have those already. Okay, so I can do that, and then I can pass you the expression that I want to evaluate. Right. So I need to create a context. create a context. Then I can do constant eval. I'm pretty sure I have a function. Yeah, constant eval. It takes the constant and the expression. Auto data eval context expression. And then I'm essentially doing that. Or rather, let's make it proper. So the actual type that we're getting is a loud one-time value result. We can then mem copy the data into the result and get that as a size t. Like so. This of course means I need a VM now during compilation. Which is a bit annoying on a like dependency sort of way, right? Because compilation requires codegen and code, so it's not like it's a bit of a mess in the dependency graph. The VM needs to be stored in the state, so we get access to it. So we store the VM, and then I include codegen. And then I need to, when I pass a declarator, right here we need to do constant evaluation. Right here. Size, cloud constant eval integer expression in the VM, in the AST of expression. And then I get the size. And that. Right, I need the VM. Right. So the issue here is we're getting an expression that's not linked into the tree. So we can't actually traverse it yet. That's a bit annoying. That feels to be an API limitation. Because we're also like, we're about to discard the expression anyway. Yeah, so right here, we want to traverse it, so we require that it is linked in the tree. Can I turn you into the root node? So when what I'm doing at the very end is I set the root of the tree, and at this point it gets linked. And that's a private API. So I need to call that function to sort of link it into the tree. Or alternatively, I need to support traverse range for nodes that aren't linked in the tree. But that's a bit messy because it messes like the invariance, because yeah. So this is really messy. So we get an expression that is stored in the AST, but nothing actually in the AST refers to that expression, right? Because we're only storing the size and not the expression itself. We're discarding that. So it might make sense to have some sort of API like leak node or something, which takes the expression, links it, turns it into a sort of like dummy root node that can't be accessed by anything else. And then we can use that. And I think such an API actually makes sense. So let me sneakily add that locally. So we've got nodes. Right. So what I'm thinking is leak node. Set next parent to n. And then I make you a friend. And that should do the trick. Right? Yeah, it takes a node kind. So then it essentially turns the node into a self-contained thing. Okay. So we need to add that to try it later on properly, but for now we get array of the correct size after we doing constant evaluation. So then of course we get an assertion failure during CodeGen. So let's CodeGen for that. And I know exactly where we're getting the assertion failure when we are asked to CodeGen a type. We are switching over the types, but we don't support array types. And here's the thing. lvalue doesn't do array types. Because lvalue is a stack-based. So it works on the operand stack, and arrays don't fit on the operand stack because they're too big. So the primitive type cannot support arrays. Luckily, this isn't an issue because we're not dealing with arrays. Anyways, in C, we're only dealing with pointers to the first element. We only need to actually deal with arrays to resolve space. But then we don't need the type, we need its layout. So, and layout can be arbitrary. So what we need is CodeGen layout. And here we're doing, if we're having an array type, so if we're having an array type, then we can get the layout. Otherwise, CodeGen is at this type and return the layout of the type. Because each type has a layout. Okay. And what we're doing here is love array layout. So we get the element layout recursively. Of the element type, element layout, and then its size. Okay, and now we need to look at all the places where we are calling CodeGen a type. So here we need an actual type. And so do we here, and so do we here. Yes, the lvalue of then we also need the type. But for a type constant expression, we don't actually need the type. We need the layout. Load the value stored at that point. For loading it, we need an actual type. For loading it, we need an actual type. For loading, we need a type. Here we're also loading. For global, we only need the layout. We are storing, so we need the type. CodeGen type of a declaration. Then we actually only need the layout. So here we need the type when we have an initializer. Then we need the type. But here we just need a layout to actually create space for that. CodeGen layout. And for constant eval, we need the result, also need the type. Okay. And now we're creating local storage for 88 bytes, which is 11 times 8. So 11 things. So we're creating enough storage. So that is good. Yeah, I'll add that to Dryad off stream later. So let's commit for now. Add array types and declarations. Okay. So the next step is to actually start using an array. So we want to do something like that. Right, invalid type for subscript operator. And for unary operator. Interesting that we're getting 2 errors here. So let's tackle that. And the trick is in the lvalue conversion. So, because the standard says when we're having an array that we are not using as a size of or line of, it implicitly converts to the first pointer to the first element. So, if so what do we do? So let's say if we have an array is node has cut. So if we're having an array type, then we convert to a pointer to the first element. And for that, let's also reuse this conversion instead. But instead we are getting a pointer type out of it. Try cast, then array type, element type. So auto pointer type. So we need a pointer to the first element. Types dot create. Not create. I can't use create. I need to use build. What's it called? Lvalue type forwards node creator creator. So we create a pointer type by cloning the element type. Then pointer type. That apparently, right. That's true, but we are not, so that's correct, we're just not calling it for subscript, because subscript expects an lvalue. So we need to actually do a separate function. If the expression has array type converted to pointer to the first element, let's call it to array decay. So do array decay like so. So this also needs to do array decay first. And then let me have it like so. Okay, and then I need to look again at all expressions. Language server type. So let's look at all expressions where we need to do array decay if necessary. So for the address, do we need to do array decay before? I don't know. Let's check the standard. Except when it's the operator of size of, type of, or address of. So address of, we don't do array decay. But for dereference, we are doing lvalue conversion, which does array decay. For L0, we're already doing lvalue conversion. For increment, right, here we definitely need to do array decay. Because the only thing where we're not doing array decay is for size of, type of, or address of. So child do array decay state log child. Okay. Cast assignment also does array decay. So when we do assignment, on the left we're doing array decay, which also, like, we're doing array decay, so we convert an array into assignment. So we convert an array into pointer to the first element. But you can't assign that because that's not an lvalue. So the point is that we're doing array decay here, because it will always make it incorrect if it actually gets triggered. Hi, thanks for stopping by the stream. So that is that. Let's see. I'm not sure where subscript is actually handled. I believe it's Unary. No. So subscript operator. Ah, right. Right here we need to do array decay. State log pointer. Why are you not a pointer to the complete object type? We did do array decay, so you should be a pointer to the complete object type because we're creating a thing. Let's disable that check for now and see what happens when we print the type. We're getting another error for invalid type for unary operator. Let's disable that for now as well. Let's see what we're actually getting out of the AST for now. We're getting a back assertion thing here in deref. But we're doing an lvalue conversion in the thing. Right. So we're doing an lvalue conversion on the child. This should convert it into a pointer type. Because lvalue conversion does array decay, which creates an lvalue conversion expression which has pointer type. So why are you not of pointer type then? So that's weird. Let's see. It's a bit tricky to I know what I can do. I can dump the type. No, that is not public. So let's make it public. Dump type. Okay, so here I want to dump the type, please. Of the child. So the first thing that we get before failure should be the type of the array. Except standard out wasn't flushed. So let's do that. Something 64. Yeah, that's incorrect. That is in fact not a pointer type. I believe I know what the issue is. So when we do a subscript, right here, we're saying if the pointer isn't a pointer, then we swap it around. So the pointer's always on the left, because pointer index, that's actually commutative. So we can use the index, so you can write something like 0 array. This legality. So we need to swap it around by checking whether that's a pointer, but it is not a pointer, so we swap it because it's an array. So let's handle that. So now array type. Can you? Yeah, I believe you need the unqualified type here. Okay. And then if it's neither a pointer nor an array, then we swap it around. And then I believe I can also get rid of those checks. Except I need the same one here. Because now it should work. Right. So we've got an assignment expression on the left-hand side. We are getting an array. We are doing an lvalue conversion to pointer to signed in 64. We are adding the offset 0. We are dereferencing that, and we are assigning that 1. That is correct, except we're not handling that in CodeGen, I'm assuming. So, and I believe it should be the lvalue conversion expression. No? I mean, this... let's actually see. Always nice to see a libc here. CodeGen, right. Because we've got an identifier expression and we try to get its type. We want to get the address, but we don't have a type, so we can no longer return the type. That shouldn't be too bad. So because we can get the what we're doing assignment expression, we can get the type separately. CodeGen type expression left type. Right. And now we get an error for an invalid address. So let's see what we're actually doing here during CodeGen. So line 4. We are pushing 1, that's the value we are assigning. We are getting the, we're loading the local value 0. Now that is incorrect. We want to get the address of the local 0. And this is because the lvalue conversion expression. We are using that for two things. We're using that both to actually load the value, and to do pointer to array decay. So we need to like sort of detect that, and we can detect that by, so if the type aren't the same. So if the types aren't the same, the type of expression type and expression child type. That's a bit of a hack. So let's actually make it a property of the thing. Bool is array decay conversion. I think it's cleaner if we don't create a separate expression kind. But okay. So it's an array decay conversion if the types aren't the same. Our type and the type of the child. Or an array into a pointer to its first element. And let's just call it decay expression instead. I mean, it's also wrong because like the regular decay of L value to R value isn't a decay, it's an L value R value, but okay. So if it's an array decay conversion, we already get the address, so we don't need to load it. If it's a function, if it's an array, it's decaying to the address. So if we don't have array decay conversion and we're having a complete object type, then we do a load. And this looks good. We're getting the address. We're doing the offset with 0. We're dereferencing it. We're storing. Then we're doing nothing with it. So let's add a print. Clove print array 0. And we get 1. So that's array access. I believe we also need to rename. So it's still called L value conversion in the AST. L value conversion. Let's call it a decay expression. I mean, the name isn't quite right, but I don't care. Okay, so that is arrays. We can now create an array by allocating storage for it, and then we can dereference and store things in it. Let's do that. So we should also be able to dereferencing it, right? And we should be able to use it in a size of expression without decay. And we get 88 bytes because we're not decaying it. So that's great. Let's commit that. Add array access. Okay. Now there are a couple of things I don't like about the implementation at the moment. So in general, I don't like the fact that we need to do like constant evaluation during compilation to get the size of the array. This doesn't nicely separate like concerns that because like there isn't compiler depends on codegen, which it shouldn't. But okay. What we can definitely do is make it more efficient. So for starters, we're returning a vector of unsigned char of the bytes of the constant. But we don't actually, like we know statically how many bytes we have. So the general purpose constant eval needs that, but not the regular one. So let's add like an implementation helper we can call. So let's copy that. Constant eval impl. You get like data in here. And then we are adding storing you into data. data type layout size, like so. And then here we can now call codegen impl, constant eval impl result of data context expression. Okay, and here we can similarly do constant eval impl and directly store that in result. So all seems to work. Let's just add a more complicated thing. Right, so we're getting like 112. It's probably 14 by 8. I don't know, but appears to be right. Okay, so this one still works. Then we can further optimize. Like in the common case, it's an integer literal. So now try cast seed of integer constant expression. Then I can just return it directly. Right, no need to do any complex constant evaluation value. Cast out to size t. So now we have 11 again. We don't need to do constant evaluation. So let's do that. Optimize integer constant evaluation. So, and then we have an issue that's really annoying. So we can have const expr int I equals, let's call it size, 11 array size. This crashes. This crashes because we're doing constant evaluation without having done the, like at this point, it is not available. The size object, when we do, isn't available in the module because we're creating a brand new context that doesn't contain all the forward declaration yet. And yeah, so like to do every constant eval integer, like we would need to generate the forward declarations for everything until that point. And that really isn't nice. So we sort of like need to really interweave compiler and constant evaluation with that approach. So it might actually really be better to, instead of evaluate the size at this point, because we don't really need it in the compiler. We only need it doing codegen, but at that point we can safely do constant evaluation. So if you don't evaluate the expression and leave it as a parameter, so we pass the expression as a parameter, it would be a lot simpler. But then we also need to do like equality for expressions and hashing for expressions due to the way that types are inserted. And that is really annoying. So actually, maybe we don't. So like we only need to do hashing and evaluation, right, for interning as an optimization. So here we can just say that compare the identity of the expression and not the value. This would work for interning. But when we ask whether or not two types are the same, then we definitely need the size. So that's a bit of an issue. This is something I have to think about. So I've been streaming for quite a while. And I mean, we added we made a lot of progress. We added arrays, but this is definitely something that we need to tackle and need to think about the best way to solve it. So that's something I'll do next week, probably when I stream again. And until then, thanks for stopping by.